For more than a century, one material has been at the heart of modern civilization: steel. It is inside skyscrapers, bridges, cars, ships, trains, machines, power plants, and even the infrastructure behind modern technology. But there is a huge problem hiding behind all of that steel, making it traditionally requires enormous amounts of energy. And a major source of that energy and chemistry has been coal. So engineers are now asking a difficult question: can we make steel without relying on coal? The answer may come from something that doesn't look anything like a steel-making material: hydrogen. And the process is called hydrogen direct reduction, or hydrogen DRI. It could fundamentally change one of the world's oldest heavy industries. To understand why, we first need to understand how conventional steelmaking works. Steel begins with iron ore. But iron ore isn't simply a pile of pure iron. The iron is chemically bonded with oxygen. So before engineers can turn it into useful metal, they have to remove that oxygen. This process is called reduction. For generations, the blast furnace has been one of the main machines used to do this. Inside a blast furnace, iron ore, coke made from coal, and other materials are fed into a huge vertical furnace. The furnace reaches extremely high temperatures, and the carbon-based chemistry helps remove oxygen from the iron ore. The result is molten iron, which can then be processed into steel. The system is incredibly effective. It can produce enormous quantities of metal, but there is a major downside. The chemistry produces carbon dioxide, and because steel is produced on an enormous global scale, the emissions associated with iron and steelmaking are significant. So engineers began looking for another way to remove oxygen from iron ore, instead of using carbon. Why not use hydrogen? This is where hydrogen direct reduction becomes fascinating. Imagine taking iron ore pellets and placing them inside a large reactor. Instead of feeding the reactor with a carbon-rich reducing gas, engineers introduce hydrogen. At high temperature, the hydrogen reacts with the oxygen contained in the iron ore. The oxygen leaves the iron and combines with hydrogen. The result, water vapor. The iron remains behind. In simplified terms, the reaction can be represented as iron oxide reacting with hydrogen to produce iron and water. That is the fundamental idea behind hydrogen-based direct reduction. No coal is needed as the main chemical reducing agent, and instead of carbon dioxide being the direct chemical byproduct of the reduction reaction, water is produced. The iron produced by this process is often called direct reduced iron, or DRI. It can also be called sponge iron because of its porous structure. But there is an important detail. Making DRI isn't the final step. We still need steel, so the reduced iron can be sent into another major piece of equipment, an electric arc furnace. Inside an electric arc furnace, powerful electrodes create an electrical arc. The heat becomes intense enough to melt the iron. Scrap steel and other materials can also be added depending on the process. Then engineers adjust the chemistry, add the required alloying elements, and produce the final steel. So the basic pathway becomes iron ore, hydrogen reduction, direct reduced iron, then electric melting, then steel. This is very different from the traditional blast furnace route. But there is a catch. Hydrogen itself isn't automatically clean. This is one of the most important parts of the story. If the hydrogen is produced using fossil fuels, then emissions can simply move somewhere else in the system. For the strongest low-carbon benefit, engineers want hydrogen produced using low-carbon electricity, such as renewable power. One method is electrolysis. An electrolyzer uses electricity to split water into hydrogen and oxygen. The hydrogen can then be stored, transporting, and supplied to the reduction reactor. That creates an interesting industrial chain. Wind and solar power can produce electricity. Electricity can produce hydrogen. Hydrogen can remove oxygen from iron ore, and electricity can melt the resulting iron into steel. The coal-based chemistry is being replaced with a combination of hydrogen and electricity, but making this work at enormous industrial scale is not easy. The first challenge is hydrogen. You need a lot of it, and you need it reliably. A steel plant cannot simply stop whenever the wind becomes weak or the sun disappears. The industrial process requires a stable supply. That means hydrogen production, storage, pipelines, electricity generation, and steelmaking all have to work together. And this is one reason green steel projects are facing difficult economic questions. Recent developments show just how challenging affordable green hydrogen can be. For example, ThyssenKrupp's planned green steel project in Germany was originally tied to renewable hydrogen, but changing hydrogen availability and cost assumptions have led to adjustments in the project's funding conditions. So the technology may work, but economics still matter. The second challenge is the iron ore itself. Not every type of ore behaves exactly the same way. The quality and composition of the ore can affect how easily it can be processed through a hydrogen DRI system. That means the transition isn't simply replace coal with hydrogen and everything else stays the same. Mining or preparation, pellet production, hydrogen supply, reactors, electric furnaces, and electricity infrastructure all have to work together. The third challenge is energy. Hydrogen reduction requires significant heat and energy, and if that electricity is supposed to come from low-carbon sources, then the steel industry needs access to enormous quantities of clean electricity. This creates an interesting engineering connection. The future of steel isn't only about steel plants, it is also about power generation, transmission networks, hydrogen production, energy storage, and industrial infrastructure. A steel plant of the future could look very different from the giant coal-powered facilities of the past. Instead of enormous coal handling systems, you could see hydrogen pipelines, electrolyzers, storage tanks, shaft furnaces, electric arc furnaces, and massive electrical connections. But there is another reason this technology is so interesting. Steel itself is one of the most recyclable materials in the world. Electric arc furnaces can melt scrap steel and turn it into new products. So future low-carbon steelmaking doesn't necessarily depend on one single technology. Engineers can combine scrap recycling with DRI if enough high-quality scrap is available. It can be melted directly if more iron units are needed. Hydrogen DRI can provide them. This creates a flexible system. But there is still a huge scale problem. The world doesn't use a small amount of steel. We use enormous quantities. Steel is inside almost everything that supports modern infrastructure, buildings, railways, vehicles, pipelines, industrial equipment, wind turbines, power transmission systems, and countless machines. So changing steelmaking means changing one of the world's largest industrial supply chains. That's why even small improvements can have massive consequences. But hydrogen DRI isn't the only approach engineers are investigating. Some companies are exploring ways to inject hydrogen into existing blast furnaces. Others are improving electric arc furnaces. Researchers are exploring direct electrochemical and plasma-based approaches, and some systems combine different technologies. The goal is not necessarily to build one perfect process. The goal is to find practical pathways that can produce huge amounts of steel while dramatically reducing emissions. And that leads to an important question. If the technology exists, why isn't every steel plant already using it? Because engineering isn't only about whether something works. It is also about cost, reliability, scale, materials, infrastructure, energy, supply chains, and economics. A laboratory experiment can produce a few kilograms of material. A steel plant may need to produce millions of tons. That's a completely different challenge. The reactor has to operate continuously. The hydrogen supply has to remain stable. The equipment has to survive extreme temperatures. The steel quality has to remain consistent. And the final product has to compete with conventional steel on price. That's why the transition will probably take time. But the engineering direction is clear. Instead of relying entirely on carbon-based chemistry, engineers are trying to redesign the chemistry itself. And that is perhaps the most fascinating part. For thousands of years, humans have been refining ways to turn iron ore into metal. The Industrial Revolution transformed the process. The blast furnace became incredibly efficient. Modern steel plants became massive and highly automated. But now, the basic chemistry is being challenged. What if oxygen could be removed from iron ore using hydrogen? What if electricity could replace some of the fossil fuel energy? What if steelmaking could be integrated directly with renewable energy? These questions are driving a new generation of industrial engineering. And if the technology can be scaled economically, the steel plant of the future could look very different. Instead of coal being at the center, hydrogen could be. Instead of carbon being the key reducing agent, hydrogen could remove the oxygen. Instead of relying mainly on combustion, electricity could provide much of the energy. And instead of water vapor being an unwanted side effect, it could become the main chemical product of the reduction reaction. But there is no magic here. Hydrogen has to be produced. Electricity has to come from somewhere. Infrastructure has to be built. And the economics have to work. That is the real engineering challenge, not simply making one piece of green steel, but making millions of tons of it, reliably, competitively, and at global scale. Because the future may not be about eliminating steel, quite the opposite. The world may need even more steel for new infrastructure, energy systems, transportation, and technology. The challenge is figuring out how to make that steel differently. And that's why hydrogen-based steelmaking is so important. The next time you see a steel bridge, a skyscraper, a train, or a massive industrial machine, remember what had to happen before that steel could exist. Iron ore had to lose its oxygen. For more than a century, carbon-based processes have dominated that transformation. But now, engineers are attempting something radically different. They're replacing coal-based reduction with hydrogen, and replacing some fossil fuel heat with electricity. The result could be a new era of steelmaking, not a world without steel, but a world where one of humanity's most important materials can be produced with far less dependence on coal. And that may be one of the biggest engineering transformations happening inside heavy industry today. If you enjoyed this engineering documentary, subscribe for more stories about advanced materials, energy systems, heavy industry, machines, and the engineering technologies changing the world. I'll see you in the next documentary.